Hello YouTube. Today we will be covering a brief introduction to modern physics. And to be more specific, we will be covering relativistic mechanics. So what is relativistic mechanics? That just seems like a bunch of scientific lingo. Well, basically we should cover Newtonian mechanics first. So Newtonian mechanics is basically the study of macroscopic objects and how they move. So let's say we have a 5 kilogram baseball moving at 30 meters per second. We can see it, it's macroscopic, it's moving at a pretty dang slow speed. And stuff like Newton's laws can apply to it. It's Newtonian mechanics. Now, let's say we had an electron particle moving at half the speed of light. Newtonian mechanics just does not work here. It ceases to work. And for stuff like this, we need a different field of scientific inquiry. And that is known as relativistic mechanics, where we'll study the behaviors of these particles. So let's get right to it. Let's first cover a concept we know as time. So let's say we have a runner. His name is Bob. He's wearing a runner's watch. Now let's also have a stationary observer who's just not moving. Call him Jim. And then we have a wall with a clock on it. So it's been well established that Bob's clock, as he runs, will be slower than the one that's on the wall. So how much slower is determined by this formula. So this Greek looking t is the time elapsed as on Bob's watch clock, while the normal t is Wall's clock. So this is known as something called time dilation, because notice that this factors here and it will always be less than 1, unless of course Bob is also stationary, because then the velocity would just be 0. But just know that this is always less than 1 if Bob is moving. And basically this just says that Bob's watch clock will always tick either at the same speed as the wall clock, or if Bob's moving, slower. And this formula has massive repercussions. So let's say you wanted to find Bob's velocity. Would you use his watch clock's time to describe it, or the wall's clock time? Because velocity is distance traveled over time. So would you use this one or this time? Well, in relativistic mechanics, you can kind of use both. There are 2 different types of velocities. So the first one is known as the proper velocity, which I'll just call Greek n. Greek n is the change in distance, so let's just call the distance he travels s. Change in distance over the watch clock time. So this is approximately the change, delta s, the change in distance over the change in watch clock time. This is used a lot, to say the least. And then there's a second type of velocity, u, which is the one that's in here. U is ds over d normal t. So we're using the watch's clock time. Sorry, the wall's clock time. The stationary one. So we can do a little bit of rearranging to find the relationship between these 2 velocities. So we know that if we divide both sides by dt, we can get something that looks like this. then we know that u over n is equal to ds over dt over ds over d Greek t, that is equal to d Greek t over dt, meaning that this is equal to u over n. So that means that u over 1 minus u squared over c squared is equal to n. Okay, so we have this formula now. So how do we get from here to a crazy thing like mass and mass not being conserved? Well, you may remember from your Newtonian physics that there's a concept known as momentum, and momentum is just equal to the mass times velocity. So if you had, like, I don't know, a 50 kilogram ball moving at 3 meters per second, your momentum would be 150 kilograms times meters over seconds. So here we'll have the momentum is equal to the mass of the particle, and this is known as the rest mass, I believe, the mass of a resting piece of matter, because mass varies again. So mass times velocity. Now, which velocity do we use? Do we use u or do you use Greek n? Well, u is pretty much the Newtonian velocity. That's not really a relativistic velocity. U is just the one that a stationary observer looks at. It's the one that you'll see from a Newtonian standpoint. N is the one that we should be looking at, because that's the one that is changed because the object is moving and that time is being dilated. So momentum is not equal to mass times the velocity of the moving object, but rather it's mass times the velocity of the moving object divided by the square root of 1 minus the velocity squared over, this should be c squared, the speed of light. I should note that c is the speed of light. And the reason why these effects are not noticeable are because usually objects are moving so slow that, like, this c in the denominator will just completely eliminate it. So let's say you have something moving at 3 meters per second. Well, you have 300 million, all that squared. Where's this whole term gonna go? Nowhere. Does not matter. So that's why generally people use mu or mv for momentum in Newtonian mechanics, but just know that it's not actually that, it's this. So, where can we proceed from here? Well, Einstein actually came up with an astounding result where he found that energy was equal to this momentum multiplied by c, or speed of light. So if you're able to multiply these two together, you'll find that this is equal to mu c over 1 minus u squared over c squared. Then this can turn into c. This becomes mc squared over square root of 1 minus u squared over c squared. So this is kind of looking eerily similar to the E equals mc squared that we see everywhere. It's its most famous equation. So how do we get from here to E equals mc squared? Well, you have to remember that when an object is at rest, u equals 0, or v equals 0, but we'll call it u equals 0. So this makes this term 0, making the rest state something known as the rest state energy, mc squared. So if you have a resting piece of matter, it has an intrinsic energy that is equal to mc squared. Now, there is going to be a different formula for when the object is actually moving. It's not still going to be mc squared. Rather, it's going to be E kinetic energy equals E total minus the E resting energy. Because the thing is, when an object is moving, it still has that intrinsic resting energy, but now it has kinetic energy. So you could kind of think of it as E kinetic plus E rest equals E total, and then that becomes that. So it doesn't look like I skipped too many steps here. So E kinetic energy is equal to E total, which is going to be mc squared times 1 over square root of 1 minus v squared c squared, or sorry, I keep mixing up my u's and v's, u squared over c squared minus 1, because this is the resting state. So where do we go on from here? Okay, so let's proceed on. So remember that the total energy in a piece of matter is going to be that thing that we had earlier times an extra c, and then times mass. So kinetic energy is the total energy, which is that, subtracted by the rest state energy, which is the famous formula we all know, mc squared. So kinetic energy is mc squared over 1 minus square root of 1 minus u squared over c squared minus mc squared, or mc squared times 1 minus 1 over square root 1 minus u squared over c squared minus 1. And this formula here has really interesting repercussions. Like earlier, I said that earlier, I keep repeating myself, but it's all really interesting. I mean, if you made it this far in the video, then you have to be fascinated, I'm sure, by this topic. So you can expand this into a Taylor series, and you'll get something like this: 1 plus 1/2 u squared over c squared plus 3/8 u to the 4th over c to the 4th minus 1. And here, the ones cancel out, so we're kind of left with mc squared times 1/2 u squared over c squared plus 3/8 u to the 4th over c to the 4th. And there's other terms, like there's negative 5 over 16 u to the 6 over c to the 6, but it just becomes insignificant, so I'll just put a ... there. And then this, my friends, becomes 1/2 mu squared plus 3/8 u to the 4th over c to the 2nd power. Now, and then ... Now, if u is a really small value, so like it's significantly less than c, then this term and all the future terms, since all the future terms have c in a denominator, they kind of just approach 0. They're just really small, pretty much insignificant. We're left with 1/2 mu squared, and that is the kinetic energy formula for macroscopic objects. So, don't you think that's crazy how we're able to, derive a Newtonian mechanics formula from relativistic mechanics. But we're not quite done here. Okay, before I leave you to go off and ponder on about how crazy physics is, let me just show you one last example to solidify the fact that classical mechanics is absolutely bonkers. Sorry, relativistic mechanics is absolutely bonkers. So, let's say you have two masses m. They're moving at, I don't know, a casual 3/5 the speed of light at each other. And when they collide, they stick to each other. And they create a bigger mass m. So my question is, what is the mass of the new lump in terms of m? Wouldn't it just be 2 little m? That's the logical answer, right? That's what classical mechanics tells us. Wrong. And I'll tell you why. So, the total energy of either ball before collision is going to be E total equals mc squared over 1 minus, well, u is 3/5 c, so 3/5 c goes here, squared over c squared. So that is equal to mc squared over 1 minus 9 over 25, or mc squared over 4 over 5, or 5/4 mc squared. So that is going to be the energy as the mass travels forward. So after these two combine, it's not like they go bouncing right back. The energy has to go somewhere, so it's all converted into rest energy. So energy's still there, it doesn't go anywhere. So E total becomes, so the E total of both masses combined is 5/4 mc squared plus 5/4 mc squared, because that's energy of both balls combined. That is 5/2 mc squared. What? Well, what is that? How is, so this is confusing because the rest state energy of big M is mc squared, as per Einstein's famous formula. But you have to cross out the c squared, so you end up with big M equals 5/2 small m. And this is a true statement. It was proven with postulates and basic algebra. So what went wrong? What the hell? Where did the extra 1/2 m come from? Right? Because logically, this would just be 2 times small m. Why is it 5/2 m? Well, this is what classical relativistic mechanics gets us. And, you know, from a, I don't know, another standpoint like classic physics, classic mechanics, you might think, well, no, dumbass. All the energy went into thermal energy. It did not go into normal mass, or it did not increase the mass. Mass should be conserved. But that's not what relativistic mechanics tells us. So this has huge repercussions, right? Because wouldn't like hot water be heavier than cold water, even though they should have, if you have like apparently the same mass, hot water is actually a little heavier. A compressed spring is heavier than an uncompressed spring. So I don't know, this is crazy stuff. So I encourage you to think about it, and thank you for watching.